So I have a flight to London at 3, so I have a hard stop in about 30 minutes. If you have questions, you're welcome to email me and I'll answer them if I can. So what I'd like to talk about today is a project that I've been working on for 15 years. It started at the University of Texas. This was a DARPA-funded project. It was the largest grant the CS department at UT ever received, $17 million. The PIs who started it were Steve Keckler, who's now the head of NVIDIA Research Austin, Doug Berger, who's my manager at Microsoft, and he's mainly involved with the Brainwave project, which our previous speaker talked about. That's accelerating neural networks on FPGAs. So it's hard to go through 15 years of work in 30 minutes, so I'm going to hit the highlights. And so what I'm going to be speaking about is an alternate form of instruction set. This is a data flow processor. So what this talk is not about is anything interesting today. It's not about AI, ML, data centers, the cloud, FPGAs. It's about CPUs and ISAs and compilers, things that we used to be interested in. And so I think we can declare that Moore's law is dead, but don't worry, it's not going to affect us for a while. We have a decade of just improving algorithms and tools before this is really going to come back and haunt us. There's the explosion. And so we've been on this paradigm called the von Neumann model for quite a while. Why the von Neumann model? Because its name was first on the paper. But this is the idea that you have a store, right? You load something from the store, you store something to the store, and that's called the von Neumann bottleneck. And so today we have RISC, CISC, and VLIW processors. I put the asterisk next to VLIW because it's not used as a general purpose core, although we certainly tried with titanium. But really, these are all fairly similar, right? These are von Neumann models. So what I'm going to propose to you today is that there are alternatives out there, namely data flow. And this was quite popular to look at data flow architectures in the 70s and 80s, and it kind of petered out in the 90s. And so I won't claim that we have done anything drastically new. We kind of rediscovered old techniques and modernized some of them. And so the name of our instruction set is called EDGE. It stands for Explicit Data Graph Execution. This term comes from Chuck Moore, who's no longer with us. He was a collaborator at UT when he was at IBM Austin. And so what EDGE is it's a hybrid data flow instruction set architecture. So there are still loads and stores to memory. But we introduce a third namespace called temporaries. And so if I have this simple example here, so we have these RISC instructions, add R1, R2, store them into R3. We're going to turn this into an explicit graph. So the T's are now temporaries. These are not registers. They're some kind of scratch pads that you cannot address. The compiler builds a dependence graph from the instructions. Here's our simple graph, and the blue edge is to highlight the temporary arc. And this graph is communicated through the ISA, right? And so why do we want to do this? Well, an out-of-order processor is rediscovering this graph at runtime. It's quite inefficient. The compiler already knows it, so why don't we just communicate it? So if we look at our data flow instruction set, you'll notice a couple things, that there's a lot of source operands missing. That's because the source operands are implicit. So for example, if we look at the add instruction, I3, it only has one source operand, but that's not a source operand, that's the destination. So the microarchitecture knows an add is a binary instruction. It needs two source operands to execute. When it receives two source operands, it wakes up and fires. So that's data flow in a nutshell. And so there's no registers in this graph except at the leaves. And so we have special register read instructions. There is a register file to read the register values and inject them into the graph. But the registers only communicate between the subgraphs. So it's pure data flow computation within the graph. And so the compiler's job is to form these graphs, try to make them as big as possible, try to expose as much ILP, and then the hardware executes them. So how do we build a large instruction window? Here's just a simple fur filter. From rolled it a little bit, looks like this. So here's one iteration, second, third, and fourth. And one thing to notice is the blue arcs. Those are the register values we're communicating between the subgraphs. But inside is pure data flow communication. So we're not going to the register file. We're just passing the operands point to point. And so that's very efficient. And so the first version of this was called TRIPS. That stood for the Terop Reliable Intelligent Processing System. This was a DARPA-funded project. We built a dual-core processor at UT Austin with the help of IBM. And this was a tiled machine. So you can see the tiles in the picture. What does that mean? That all these tiles are connected by a network. So there's execution tiles, which are your function units. There's register tiles. There's data cache tiles. If you want to expand the microarchitecture, just keep adding tiles to the network. Now, of course, the compiler needs to find ILP and instructions to place on that. But if you go back into the early 2000s, what were people after was high-frequency, deep pipeline machines. And one of the problems was, how do you build like these very aggressive microarchitectures? So this was our solution, build a distributed microarchitecture. And this was one of the most complicated processors ever built in academia, and one of the last serious efforts in academia. It's just too time-consuming and expensive these days. So one thing to notice about this, or to note about this, is that we've exposed the reservation stations to the compiler. So this is a spatially scheduled design. So the compiler decides where to place the instructions, and then they execute naturally in data flow order. And so the advantage of data flow is that it's an out-of-order execution model. So you get out-of-order execution for free, or close to free, and with near in-order power efficiencies. So here's the nice picture. Okay, so that was the first like 10 years of the project, or 8 years. So around 2008, I joined Microsoft, and I was the only one of the team that was interested in continuing this work. And so TRIPS was the name of the first ISA and the first processor. And then at Microsoft, we did 2 different designs, the MSR v1 and the MSR v2. And so just summarizing some of the differences in the instruction format. So with TRIPS, these were 32-bit fixed instructions. That makes sense. That's not unusual. The subgraphs that we were building, those were up to 128 instructions. And if the compiler couldn't find 128 instructions, it padded the graph with no-ops. And those no-ops were fetched, so it was quite inefficient. We put metadata on these graphs, like how big is the graph. We encoded the register reads and writes in this metadata. That metadata was quite large, 128 bytes for each of these graphs. And then we banked the register file. And that's because of this tile design. We wanted the register banks to line up with the execution units. So we didn't have any SIMD. It was spatially scheduled. We didn't really think about the exception model too much, which is important if you want to boot an OS. So it was block precise, meaning if your graph threw an exception, I could tell you that graph had an exception. I wouldn't necessarily be able to tell you which instruction had that exception. And so OS, we knew someday we'd boot an OS, but we never did it back at UT. So then I joined MSR, and the first thing I did was port Visual Studio. So I wanted to have a production quality compiler, wrote a new simulator, started porting applications, started looking things like HoloLens, image processing kernels, Connect body tracking, things that were important to Microsoft at the time, and came up with this new MSR v1 ISA. So this was based on the work from UT, because that's what I knew at the time. And so started to fix things though in the ISA. So first of all, the graphs are now variable size. So if the compiler only has a 1 instruction graph, that's fine. It's not padded with no-ops. Next thing, start to reduce the metadata. So the block header, shrinking that, instead of 128 bytes, brought it down to 16. In the current version, it's 2. We're planning to make it 0 soon. And then unified the register file. And the reason I unified the register file was I got rid of the spatial scheduling. So it's not a spatially scheduled machine anymore. It's just a RISC processor executing a graph. That's one way to think about it. Introduced some MMX-style subword SIMD. Now we're going to the ARM-style variable length SIMD instruction set. Changed the scheduling to dynamic from spatial. Didn't do anything about the exception model at that time. Started to think about it. Started to work with the Windows kernel team to bring up UEFI. So that's the secure bootloader. That's the first thing you need if you want to boot the Windows kernel. And around this time, started to work with Qualcomm research to actually prototype some chips. And so the MSR v2, this is the collaboration with Qualcomm. So first thing we wanted to address is code size. So code size is very important, especially in a data center environment. You don't want to pollute your iCache. So we started to reduce the instruction format even more and went to this 16-bit base instruction format that I'll explain in a second. Kept the variable size blocks, shrunk the metadata a little bit more, kept the register file at 64 entries, didn't do anything about the SIMD model yet, didn't change the scheduling. But because we wanted to boot an OS, we need to have instruction precise exception support. So we introduced a model for that, which I'll explain. And then we ported Windows 10 Linux and FreeRTOS. And so let me talk a little bit about this MSR v2 instruction set. So this is a 16-bit base instruction format. So it's variable length, but not in the way that you're thinking. And I'll show on the next slide what I mean. So the block is a meta instruction. So you can just think of these subgraphs as instructions. They have some inputs and have some outputs, and they're atomic. Either that graph executes or it doesn't execute. Most instructions support up to 64-bit immediates. I'll show you how we do that. That's kind of unusual. And this is a data flow instruction set. And so the compiler will form these up to 128 instruction graphs. We sometimes call those blocks. That's what gets executed by the microarchitecture. Registers are used to communicate between these graphs, but not inside of them. So if you write a register, you cannot observe that write yourself. There's register read instructions to read the register file. There's still loads and stores to memory. Unfortunately, we didn't solve that, so it's still a von Neumann memory model. And then this is a general purpose core. People often think of this as an accelerator. This is not an accelerator, although you could use it as an accelerator. I mean, it boots major operating systems and supports imperative languages, out of order programming, and whatever you want. So here's just the base instruction format. So the orange is the 16-bit format. So there's an opcode, there's a predicate field. Every instruction can be predicated, but this is not a VLIW predication model. It's a data flow predication model. You can read the Micro 2006 paper. So there's something called a broadcast ID. So in data flow instruction sets, you have this problem where you need to encode the target. Where are you going to send the value? So that takes bits, right? If you have a stack pointer that you need to fan out to 20 consumers, you need encoding space for potentially 20 consumers. So of course we don't do that. We fix it at 2 targets. So if you have a bunch of consumers, you need to build a fan-out tree. So that lengthens the critical path, increases the dependence height. You don't want that. So the broadcast field, that's exactly what it sounds like. We can just broadcast values out on channels, and you can subscribe to listen on that channel. So we support 3 broadcast channels. And then in the gray, these are the optional fields. Well, sometimes optional and sometimes required. So up to a 64-bit immediate, extended targets. And so, for example, of an extended target, I want to write register R3. You would encode it in that extended target field. And extended opcodes. So there's lots of opcode space. So the instruction format is what we call a block instruction format. It's a little bit different than anyone's ever seen. So we use this graph as a container, or this block as a container. And so we take the 16-bit base instructions, and we lay them out contiguously. So that's fixed length. I can decode those, right? I know they're all 16 bits. Very easy to decode. But if I give you an example, we use the rest of this block or this container for the other parts of the instructions. So the instructions are not contiguous. The only way to decode one of these graphs is to start at the beginning and go to the end, because I need to compute the offsets to all the sections. So for example, I have an add immediate of 1024. That 1024 is not in the orange part, it's in the purple part. And so to figure out the offset in the purple part, I have to decode all of the orange part first. Likewise, for extended targets, there's a section for that, and for the extended opcodes, there's a section for that. And why do we do this? It's for code size, because we want to be very dense in our encoding. And you might say, why not just build a variable length instruction set? You could do that. Intel has certainly shown that variable length ISAs are not that difficult to deal with, but we don't want to deal with the area complexity, the decoder complexity. We want to have the advantages of variable length without the disadvantages. So that's where this comes from. So how do we support precise exceptions in this model? So I'll walk you through an example. So this graph is going to read R1, R3, and R5. So the first instruction just reads R1 and writes it to R3. This write to R3 is buffered. It's a transactional model. If this block tried to read R3, it would get the original value of R3, not the value of R1. So there's a load, and what happens to the load? We're going to cache the load in something we call the PBR. It stands for partial block replay. And so effectively what we're going to do here is we're going to cache all the loads and stores, all the memory instructions, and then we're going to replay them on an exception from that cache. So this load goes to memory, value comes back, we cache the load in this load store queue. There's another read of R3. This is not the value of R1, this is the original value of R3. There's a store, that store executes, it's also cached in the PBR. And now there's divide by 0. It's just an example. Let's not argue whether or not divide by 0 is a real exception or not. Divide by 0 happens. So immediately, this graph, this block is done. There might be other instructions to execute, but we're not going to execute them. So at this point, all stores are going to be committed to memory. They become visible. The register writes that have been buffered are going to be thrown away because we're going to re-execute them. And so at this point, you transfer into the exception handler. Somehow it fixes the divide by 0. And then we're going to replay the block. So starting again, we read the value of R1. We haven't changed the register file, so it's still going to get the original value of R1. The load is not going to re-execute. We're going to take the value of the load from the PBR. So, if you have strongly ordered memory, some device, keyboard, for example, I can't go and reread your keystroke. I've already read it. So whatever value that load had before is the value we're going to return here. Read of R3, store. The store doesn't execute. It comes from the cache. Divide by 0 has somehow been magically fixed. Now the graph continues executing. And now we have a new memory instruction. This could cause an exception also. So now we're going to buffer this also in the PBR, and so forth, until the graph completes. And so the advantage of this model, compared to, say, you could transfer in the context of the OS all these temporary values that have been stored. The advantage of this is that we don't have to cache that many temporary values. So it's more area efficient. The disadvantage, though, is that I have to replay the graph. Whereas if I transferred in the context the operand buffer values, maybe I could just start back at the point of the exception. So this works. I can prove it works. So here's Linux. This is a very short video. So this is Linux with BusyBox. So first thing that happens is U-boot runs. It basically does a mem copy of the Linux kernel. Sorry if it's a little fuzzy. So this is compiled with LLVM. So we have both a Visual Studio compiler and an LLVM compiler. You can see some processes, who am I root, some BusyBox commands, do a little VI. Not a very good typer, sorry. And I don't know VI, as you're about to find out. How do I get out of this? Oh, I'm already out. And so we have some games. So we have the first game, Canonical Cave Adventure, go into the cave, get the lamp, turn it on. We have Pac-Man. We're working on binary translating Doom at the moment. So that's Linux. So of course we also have Windows. And so Windows is much more complicated to bring up than Linux. Linux itself is just a kernel. Windows is a UI and solitaire and a lot more going on here. And so where's the rest of Windows, like the start button? Well, that's a whole other layer of the onion. So we boot to a command prompt, and then we run things from the command prompt. So there's solitaire. And so a summary of what we've done at MSR, I guess, in the last 10 years. Ported Windows, ported Linux, ported FreeRTOS, brought up Visual C++, brought up LLVM. We also ported Core CLR. That's our cross-platform C#.NET. We have a full system cycle level simulator that can boot all these OSs. We have C++ and C libraries. And so let me talk a little bit about what we did with Qualcomm. And so this is a 5-year collaboration with Qualcomm Research, so led by Greg Wright. So Greg is now the head of Qualcomm Research North Carolina, I think. But when we met, we were both just researchers at Microsoft and Qualcomm, and we said, let's collaborate. And so why was Qualcomm interested? Well, they were interested in building an energy-efficient, out-of-order CPU. And so they wanted to know, could this ISA maybe enable them to do that? And so in a conventional and RISC ISA, this doesn't reflect the reality of what's going on in an out-of-order processor. So the front end reconstructs the graph, right? But the compiler already knows this graph, so why not just communicate it and save all that area, power, time? And so our thought was a well-matched ISA would allow the compiler to express the graph and then allow us to run high-level languages and conventional software that we know today. So we're not trying to change anything, right? People often ask, why don't you use like a functional language or some different language? Find more ILP or research ideas. And that's great. I encourage researchers to go do that. But I want to have a general purpose processor that can run the software stacks of today, but maybe more efficiently. And so the benefits we thought was improved power and performance, so performance per watt, with minimal changes to the software stack. And so that's what we set out to do in our research collaboration. Can we build an edge processor with a full SoC that doesn't require us to change the world? And so some of the advantages compared to a conventional out-of-order pipeline. So we can do out-of-order fetch because in the ISA we communicate the size of these graphs. So I can fetch the graph out of order. There's no register renaming because the compiler has done all the register renaming for you and expressed it in the ISA. A lot of CAMs are turned into RAMs, which hardware people like. And most results do not write to the register file because it's point-to-point communication. So those are just some of the differences. So we prototyped 2 cores. We did not tape them out, but we went all the way through place and route. So we did 2 designs, what we call R0 and R1. So R0 was to compare to a little ARM core, and R1 was to compare to a big ARM core. And our target was 2+ gigahertz in 10 nanometer. And so the parameters for R1, so this was a 128 entry instruction window, and we divided it into 32 instruction segments, and we picked 2 instructions for each of those segments. So it's an 8-wide machine. So in the same area of an in-order Qualcomm Snapdragon little ARM core, we built an 8-wide out-of-order processor. Here's a floor plan, taken all the way through Qualcomm's commercial process. Didn't tape it out. Closed at 2.1 gigahertz. I think that's the important thing to say here. And so then we wanted to scale this up. So if we want to build an even more aggressive design, what did we do? Well, we just took these 32 instruction slices and we just replicated them. So instead of being 8 wide, we're now 32 wide. We have a 512 entry instruction window. This is not a balanced design at all. Front end is only fetching 8 instructions at a time. We're only executing, out of this window, we're only executing 2 memory instructions. That's just because we were running out of time for the research collaboration. So this was pin-for-pin compatible with a Qualcomm Snapdragon SoC. So we take the ARM core out, we drop our core in. And this closed at 1.9 gigahertz, but I think the number was more like 2.1 after these slides were made. And so that was a dual-core, cache coherent processor. Uses the same memory system as the Snapdragon core. So these are Qualcomm's results. They're only results I'm allowed to share. So this is spec-int performance based on their performance model. That model has been tuned against their RTL. So little and big, those are commercial Snapdragon cores. Can't tell you what the names of them are because I don't know, but we can assume that they are what you would go buy today in an Android phone, or maybe 2 years ago. So R0, not sure how to use this. Well, so R0, when we first compared it to Qualcomm's commercial core, it's a little bit slower, but then we did some improvements to the microarchitecture, and we were starting to be like 10, 15, 20% faster. The big core, also a little bit slower when we first started. Then we made some improvements to the microarchitecture, and we start to hit the same results as them. And so that you might say, well, why aren't you exponentially faster? It was a very small team. Hundreds of people working on these, Snapdragon cores, 10, 20 people on the research project with a very short amount of time. Also, this is about performance per watt. So we're more power efficient than these cores because of the ISA. So I don't have power numbers because I don't believe that unless you tape out a core and put some power pads and measure the power that there's much to say. So if you don't know how these power models are built, you take a physical thing and then you build a power model based on that physical thing. So when we looked at power, of course there are tools. Sometimes power was like half the power of the Snapdragon core. Sometimes it was orders of magnitude larger, which doesn't make any sense. So don't want to show power numbers today. So, but what do all these results mean? This type of limited data flow ISA is feasible. So radically different ISA and microarchitecture than what people are used to, and a small team produced comparable results to a large commercial quality conventional core. So the OS was brought up in, the design was brought up in an FPGA. So both a kind of a scaled down version that we use for testing, and then at Qualcomm they have this huge FPGA that they use to simulate their ASICs for testing. And we booted UFI and other things on that design, so we know it works. And so we thought that this was promising, at least for mid-tier. I don't know what happens when you start to get into the domain of server, because you're going to start throwing lots of tricks at the microarchitecture, which are going to start consuming more power in order to get that high-level server performance. But certainly for like a mobile device or in the microcontroller space, this is very interesting. And so we claim out-of-order performance at in-order area and power, but I think you need to build it to decide that. So conclusions, post Moore's Law, we're going to need some new innovations in architecture. We've heard today about some of those options, DNN accelerators, domain-specific architectures. Someone will come up with something. Surprising results will emerge, so don't give up. But we desperately need some new general-purpose fabric, right? I don't mean to insult computer architects, but most of the improvements in the processors we have today come from the fab, not from the computer architects. As the fabs get better, transistors get smaller, processors get faster. And this is my statement. Maybe we need to move beyond the von Neumann model. And so edge is a viable alternative. So thank you for my very quick talk. I'm going to catch my flight now.